The first law of thermodynamics tells us that energy is conserved. And because energy is conserved, that means that we could write an energy balance for any sort of arbitrary system that we're analyzing. Okay, so because energy is conserved, one can write an energy balance, and I'm typically going to abbreviate energy balance as EB. Alright, so we could write an EB for any system. Okay? System. Alright? So, to derive the energy balance, I guess, let's first, backtrack. And let's think about a material balance for a batch system. For a closed batch system. Alright? And so the way we thought about material balances for a closed batch system is on the left-hand side, we had accumulation. And that was defined as the difference between the final mass in our system and the initial mass. Right? And so that's what our material balance for a batch system was. When we do an energy balance for a batch closed system, we could start with basically an analogous concept, okay? That the accumulation of energy in our system is going to be equal to the difference between the final energy in our system minus that initial energy. Okay? All right, and so with this in mind, let's consider a system where, I'll call it system, where it's at some time initial. Okay? And so at this initial state, we have some sort of initial internal energy, initial kinetic energy, and initial potential energy. Alright, and so that's the state of our system at time initial. And then let's say to the system we, add some heat, and we also have the system do some work. Right? And so there's some sort of energy transfer going on. And so due to this energy transfer from the system to its surroundings and vice versa, what happens is that at some later time, so system at T final, the internal energy in our system, the potential energy in our system, or the kinetic energy in our system and the potential energy in our system now have different values. Okay? And so that's due to the energy transfer of the heat and the work. And so with this system in mind, let's now consider, the energy balance. And so we start with A, accumulation. It's just the difference between the final energy and the initial energy. Okay? And so the final energy in our system is just going to be the sum of the internal energy plus the kinetic energy plus the potential energy. Alright, that's the sum of the energy in our system. The initial energy is just going to be the same sort of thing. Ki and then Epi. So just to highlight it, final, and then this is initial. Alright. Now, we could rearrange this equation so that rather than just having the final terms grouped together and the initial terms, we instead group each term by what type of energy it is. And so we could group the internal energy terms together. We could group the kinetic energy terms together. And we could group the potential energy terms together. Now, one shorthand way we could write this notation, rather than kind of writing all the parentheses and stuff, is we could actually use the Greek symbol delta. So delta U plus delta EK plus delta EP. Okay? All right? And so you've probably seen this delta used before in classes, but I just want to emphasize that delta means final minus initial. Okay. All right, and so when we consider the accumulation of energy in our system, we could think of the final minus initial values of all of the energy terms. All right, so that's one way to calculate the accumulation of energy in the system. But another way to calculate it is basically in terms of the net energy transferred into the system. All right. And so when we consider the net energy transferred, all right, basically what we're looking at is the energy that's being input to the system minus the energy that's going out. All right? And so if we go back to our little diagram here, really the energy transfer that's going on into the system is basically going to involve Q, and it's going to involve W. All right? And so if we rewrite the input and output terms, right, of the energy transfer, those are going to be equal to Q and W. All right? Because Q and W describe energy transfer into the system. Right? And so the accumulation that we calculate here is equal to the accumulation that we calculate here. Right? Those are the same thing. And so what that allows us to do is we can just write accumulation of energy is equal to delta U plus delta EK plus delta EP is also equal to Q plus W. All right? And so what this gives us is the fundamental energy balance for a closed system. Energy balance for a closed. Right? And I emphasize closed system here, right? And that's because, right, I didn't mention anything about mass flow rates. Right? In fact, we're considering a batch system. Right? So there's no mass going into and out of the system. Yet, even though there's no mass going into and out of the system, we could still have energy transfer into and out of the system, though. All right? And so the energy balance we derived here is the energy balance for a closed system. All right? And it's a very important equation because you should use this equation as the basis or to start all of your energy balance calculations. And so just like the mass balance equation that we write when solving a material balance problem, when you're dealing with combined mass and energy balance problems, you must write this energy balance equation. Right? And so you must write this for all homework, quiz, and exam problems. Okay? And one thing I want to highlight before I end this video is that the two sides, they're equal, but really the directionality of the sides is kind of different. All right? And so on the left-hand side, what we're considering here, remember we have all these deltas, and what delta means is that you're considering a final minus initial state. Okay? So your final internal energy minus your initial internal energy. Your final kinetic energy minus your final or your initial kinetic energy. Okay? So the left-hand side of this equation is final minus initial. The right-hand side, though, remember, we're looking at an input minus output. All right. Right, so the energy that goes into the system minus the energy that goes out. Right, or the energy flow that goes into minus the energy flow that goes out of the system. Right? If we moved Q and W to the left-hand side, then we would be considering, an out minus an in. Right? But the fact that these are on opposite sides of the equal sign kind of means that their directions are flipped. So this is, a kind of subtle but very important concept whenever you're dealing with these energy balance equations. And we'll get practice on how to, account for the directions by doing example problems in class and also in the homeworks.